Most people overcomplicate this topic because of the way it's usually completely changes. Today, we're looking at how this actually works through it instantly. Here is the blueprint.
For nearly 14 billion years, the universe has been expanding outward from the Big Bang. From our vantage point on Earth, the cosmos looks stable. The stars rise, the galaxies spin, and the system appears permanent. But astrophysics tells a different story. The universe is locked in an invisible cosmic tug-of-war. The physical forces governing every atom and galaxy are pulling in opposite directions, and whichever force eventually wins will dictate exactly how everything ends. Look at this conceptual model of a galaxy cluster. The first competitor is gravity. Driven by mass, it exerts an attractive force, pulling galaxies inward. The second competitor is dark energy. It does the exact opposite, pushing outward, accelerating expansion and actively fighting gravity's pull. The ultimate fate of the universe depends entirely on this mechanical conflict. If gravity wins, existence ends in a crushing fire. If dark energy wins, it ends in a permanent freeze. Let's look at the first scenario. If the collective mass of all the matter in the universe is dense enough, its gravitational pull will eventually overpower dark energy. The outward expansion will slow down and then completely stop. The timeline reverses. The universe enters a phase called the Great Collapse. Instead of drifting apart, galaxies begin rushing toward one another as the sheer weight of their own matter drags them back together. As the physical space of the universe shrinks, the cosmic microwave background, the leftover radiation from the Big Bang, gets heavily compressed. Millions of years before the final collapse, ambient space becomes hotter than the stars themselves. Stars literally cook from the outside in before colliding with one another. In the final moments of this collapse, all remaining matter, atoms, and black holes are crushed together into a single, infinitely hot, infinitely dense point. Physicists call this a singularity. This absolute compression closely mirrors the state of the universe right before the Big Bang. Because of this, some physicists suggest this singularity wouldn't simply be the end. The immense pressure could trigger a brand new Big Bang, in a sequel theory known as the Big Bounce. Under this model, the universe is cyclical. It expands, hits a gravitational limit, contracts, and rebounds, reset forever by the weight of its own matter. Now we pivot to the exact opposite extreme, dark energy overpowering gravity. In this scenario, the outward push of dark energy grows stronger, forcing the universe into a state of runaway expansion. Space expands faster and faster. Eventually, the gaps between galaxies grow so large that light from one can no longer reach another. Any observer looking up would see a completely black night sky. Cut off from one another, individual galaxies begin to exhaust their resources. They run out of the gas and dust required to form new stars. The stars that already exist slowly burn through their fuel, flicker, and die out, bringing the current Stelliferous era to a close. The universe transitions into a freezing, dark graveyard. The only celestial bodies left are dead stars, like white dwarfs and neutron stars, stray planets, and black holes. Over trillions of years, even this remaining mass disappears. The black holes slowly leak subatomic particles through a process called Hawking radiation, steadily evaporating until there is nothing left. This thermodynamic chart visualizes the final mathematical state of the cosmos, maximum entropy. The top line shows energy becoming perfectly evenly distributed. Simultaneously, the bottom line shows temperature plummeting to absolute zero, or negative 273 degrees Celsius. Because the energy is completely flat, no thermodynamic work can be extracted. All physical processes cease. Nothing moves, nothing happens. Time, as a measurement of change, loses all meaning. For decades, astrophysicists debated which of these two fates awaited us. To settle the tug-of-war, they needed highly precise measurements of the universe's expansion rate to see which force was pulling harder. In 1998, they found the answer. This line graph plots time against the rate of cosmic expansion. If gravity were winning, we would expect this line to curve downward. Instead, supernovas revealed an upward curve. The expansion is actively accelerating. This is definitive proof that dark energy is overpowering the gravitational pull of matter. And looking at this widening lead, dark energy's grip is only getting stronger. This data resolves the conflict. Gravity simply lacks the strength to pull the cosmos back together, taking the fiery, cyclical collapse of the Big Crunch off the table. Barring any radical discoveries that rewrite the current laws of physics or a sudden change in the nature of dark energy, the universe has a locked trajectory. We are on the path of the Big Freeze. Our vast universe is currently on a locked, one-way trip toward a cold, dark, perfectly silent, and completely frozen eternity. It is a stark contrast to the cosmos we observe today. We live in a highly active, incredibly vibrant era filled with burning stars, with colliding galaxies, and the warmth to sustain life. The fact that this warmth is temporary doesn't diminish its value. The inevitability of the Big Freeze gives us a profound reason to appreciate the beautifully fleeting, brightly lit era of the universe we are lucky enough to inhabit right now.